In today's video, we are going over the p-series, direct and limit comparison test, as well as alternating series. When looking for a p-series, just know that the form is the series from 1 to infinity of 1 over n to the p, where p is going to be your variable for the p-series. And if your p is greater than 1, it will converge, and if p is less than or equal to 1, it will diverge. Now, the best way to think of it is since 1 is greater in this situation, it's 1 and done, so it's 1 and diverges. They both start with d. That's how I like to remember it. And then the next one is a direct comparison test. This is typically when you see the infinite series from 1 to infinity, and in this case we're going to do the fraction of 1 over n cubed plus 2. And the first thing you want to do is just look for a possible p-series, where you would just look for a major/dominant part, which in this case is 1 over n cubed. Just find the highest degree in the denominator. And when you see that your p-series is existent, you could determine what the p equals, which in this case, since it's n cubed, the p will equal 3. And from our rules of p-series, if p is greater than 1, it will converge. So this entire series converges. Now, the difference between the next comparison test is going to be a limit comparison test, where the differences are you will see a complex polynomial as your numerator or denominator, and you would not typically want to split that as it's not as easy. So you would use the limit comparison test. Now, you would have to compare a of n and b of n, where a of n is your original equation in your series, and b of n is just going to be the highest power over the lowest power, where your b of n is just going to be the highest power in your numerator and your highest power in the denominator, which in this case is n squared over n to the fifth. So you would just do 1 over 4, but since this is not our example problem, we'll just move on. And then right after that, you're going to want to find the limit of your a of n over your b of n, and we will determine that and name it as L. Now, if your L is actually a positive or finite number, which is not 0 or infinity, this test will be passed. And so if this little part of your equation converges, which is the a of n over b of n, then your entire equation will converge as well. Now, lastly is the alternating series test, where judging by just this equation alone, you can tell it's alternating series due to the -1 to the power of n, which is a dead giveaway that you're going to use alternating series. And then you're going to want to remove the -1 to the power of n and test out the b of n, which is basically just this a of n without the -1 to the power of n. Now, the next thing you want to do is find the limit of the b and n you had just found, which was just, again, from removing the -1 to the power of n, and then finding the limit of it. And you want to ensure that it goes to 0, because that will pass the first part of this test. And if it does, the next part of the test is to ensure that a of n plus 1 is less than or equal to b of n. And so if both conditions pass, the series will converge. Now, to determine whether it will diverge, you would see if this doesn't approach 0. And if it doesn't approach 0, this test fails. So it most likely diverges. And if you're confused over the a of n plus 1 is less than or equal to the b of n, I will explain that in further detail for one of our last examples. So our first problem is going to be the infinite series from n equals 1 to infinity of 1 over n squared plus 1. Now, when looking at this problem, you can recognize that there is a p-series involved, where if you just take the major part, it's 1 over n squared, which you could set as your b of n. Now remember, this 2 could be known as our p, so that means our p equals 2 in this p-series. And because our p is greater than 1 in this case, our p-series converges. And now our next step is to compare our a of n and b of n, where in this case our a of n is our original equation and our b of n is the 1 over n squared p-series. And how I like to compare these is I like to put the number 2 in the denominator and compare which one's bigger. So for example, if n equals 2, then our a of n will equal 1 over 5 and our b of n would equal 1 over 4. Now in this comparison, we see that our b of n is bigger, so that means that our b of n will always be bigger. And so this is basically stating that our original series, which was our a of n, is smaller than a known convergent series, which is what we tested with our p-series. So what you would write is, by direct comparison test, the series of 1 over n squared plus 1 converges. Now let's let our next problem be the infinite series from 1 to infinity of n plus 3 over n cubed plus 2n minus 1. Now, direct comparison test was a lot easier because we didn't have to deal with a lot of polynomials, but in this one, we have to deal with polynomials. So like last time, you're going to want to try to find a known series like b of n, where earlier we found a p-series from the 1 over n squared, but this time it's not going to be as easy. Just kidding, it's actually really easy, because all you have to do is compare the highest powers on the numerator and the denominator, which in this case is n to the first over n cubed, which when simplified is just the same as 1 over n squared, meaning that our p-series is shown. So our p equals 2. Now, because this p is greater than 1, it will converge. Now our next step is to find the limit, which is L from n approaching infinity of a of n over b of n. Now in this case, our a of n is just our original series, so it'd be n plus 3 over n cubed plus 2n minus 1 over 1 over n squared. Now you can simply just put this n squared to the top, because that's the same thing, which just simplifies to n squared times n plus 3 over our denominator n cubed plus 2n minus 1. Now remember, in this step, when we're using limit comparison test, because we did just use limits, we are going to want to find the highest powers and divide them, and then see if it's going to be positive and finite. So don't be too tripped up on this equation, because you're going to have to distribute it to get the highest power, which gets you n cubed at the end of the day. So this is just going to be the highest power in the numerator, which is n cubed, over the highest power of the denominator, which is n cubed, which if you divide n cubed by n cubed, you get 1. Now, is that positive and finite? Yes. So in conclusion, by limit comparison test, our series of n plus 3 over n cubed plus 2n minus 1 converges. And just to be clear again, if you're comparing the direct comparison test and the limit comparison test, you will want to use the limit comparison test when you have a polynomial, since finding the limit of it will be a lot easier for you, since finding the limit of it will be a lot easier. But if you just see a simple equation like 1 over n squared plus 1 or n cubed plus 1, etc., just find the p-series and determine whether it converges or diverges. Alright, so this last example is going to be the infinite series from 1 to infinity of negative 1 to the power of n over n. So just a dead giveaway, when you see a negative 1 to the power of n, just know that this is going to be an alternating series, and it's alternating because every time you plug in any value for n, such as 1, 2, 3, 4, 5, 6, they will alternate between positive and negative values. And so just like what we've been doing with the other ones, we're going to take out the non-effective value, which is just the non-altering part. So if we took the absolute value of everything, it would just be 1 over n. So that would be our b of n. And then we have to check our two conditions, which is first our limit to see if it approaches 0 when n approaches infinity, which in this case will approach 0. So this condition passes. And then our second condition is if our b of n plus 1 is less than or equal to the b of n. So to determine what b of n plus 1 is, all we do is just plug n plus 1 into our n. And since our equation is 1 over n, it would just be 1 over n plus 1 is less than or equal to, and then our original b of n equation, which is 1 over n. And also, if you recognize, this is a harmonic series as well. So I like to use the number 2 like last time. So let's set n equal to 2 and see if 1 over 3 is less than or equal to 1 over 2, which in this case, this statement is true. And let me remove the equal to underline. So it's just less than 1/2. Now, what is the point of this test? Well, it shows that our terms are decreasing. So it passes this test as well. So because both conditions pass, the series negative 1 to the n over n converges by alternating series test. And that is going to be the end of the video. Thank you for watching.